Write down kinetic theory of gases. What is kinetic theory of gases? Basically, we are trying to understand pressure, temperature, these things with the help of Newton's laws. That is, what is pressure? Pressure is what? Force divided by area. Now, how do you generate pressure then? If you have a container and gas is present inside the container, then this gas is what? Made up of several tiny molecules or atoms. These atoms, they are moving randomly in all directions, and let's say this is the wall of the container. And when this molecule comes and hits the wall, it collides with the wall and bounces back, then it will exert some force. And because of that force, we see that pressure is present on the wall. So, the thing which is pressure, which you have seen in PV equals to nRT, this pressure is nothing but rate of change of linear momentum divided by the area. Now, rate of change of linear momentum gives us what? According to Newton, it gives us what? Force. So, if you can find when collision takes place, and based on the number of collisions and all, we'll see all these things. If we can investigate all these things, we can easily find pressure with the help of Newton's laws of motion. Similarly, when we talk about temperature, I've already given you an idea of temperature when I taught you thermodynamics. Temperature is basically what? Kinetic energy. So if things are moving faster, then it's like that object has greater temperature. So temperature is all about speed or kinetic energy. Pressure is all about change in linear momentum divided by area. This is something we are interested in this chapter, which is kinetic theory of gases. So, the first thing we need is we need to define ideal gas. Everything we'll be doing will be for the ideal gas system. So, what is an ideal gas? Write down properties of this, and based on those properties, we'll talk about kinetic theory of gases. Write down assumptions for kinetic theory of gases. Assumptions for kinetic theory of gases. The first one. Space occupied by molecules. Space occupied by the molecules or atoms is much smaller than the volume of container in which ideal gas is present. In which ideal gas is present. Now what is this first point? This is your container, and in this container, if I ask you to put two balls of this size, and if you have this size of the container and two balls, let's say cricket ball of this size, then effective volume in which these balls can move around is not the entire volume of the container. Suppose total volume of the container is V, and these two balls, their individual volumes are, let's say, V0, V0. So if these balls are kept inside this container, then effective volume is only V minus 2V0. These balls can only move in the empty space which is given by V minus 2V0. But we are assuming that for an ideal gas, size of the container is so large that volume occupied by these tiny atoms, all the atoms of the gas, take them together, even then we assume that effective volume is V only. So what we are saying in this case, this is a different situation. This is for the ideal gas. Over here you are saying that V is much larger than V0. So if it's much larger than V0, then your V effective is approximately V only. This 2V0 or 3V0, if there are n number of molecules, n V0 is almost negligible. So these molecules, they have all the volume of the container for themselves when they move around. This is the first thing, and which is not something which is completely out of the range. You all know that. Let's talk about this room and the air inside. The size of the tiny atom as compared to the size of the room is something like this. And therefore, we can always say that all these molecules, they are free to move, and when they move, they can move in all the volume which is of the container. Draw these two figures and tell me, are you comfortable with the first assumption, which is that V is much larger than V0, and therefore we have all the volume for these molecules? Draw this figure. Now write down the second assumption. Separation between the molecules is very large. Separation between the molecules is very large as compared to the size of molecules, In fact, what happens, size of a molecule is roughly in angstroms, 1 angstrom, 2 angstrom type, and the separation is 20, 30, 40, 50 angstroms between the molecules, and even larger than that if you made the air or the gas thinner, or you decrease the pressure, or you increase the temperature. We'll talk about all these things. But the point is that as compared to their sizes, individual sizes, the separation between the molecules is very large. Now, this point, the second point, basically supports the first point itself. If you say that this separation is not that large, just imagine, if separation is not large, then something like this will happen. If you pack all the molecules in this form, such that separation is much smaller as compared to this scenario, then you basically are saying that the first point cannot be justified. इस सिचुएशन को अगर आप फील करो, then when I say 2V0, I said NV0. Suppose there are 1 billion molecules. If this much is the separation, then V minus NV0 cannot be approximated with V. And therefore, the second point, it basically supports the first point itself. But then why do we need the second point? Let's talk about that. In fact, write down the third point, and this third point will tell us why do we need to mention second point. Molecules, and I say molecules or atoms. Molecules of an ideal gas do not exert any force on each other. Molecules of an ideal gas do not exert any force on each other because of their large separation. Because of their large separation. In solids and liquids, this separation is much smaller, and therefore these molecules, they attract each other. But for an ideal gas, we are assuming that this separation is so large that no force acts between these two molecules. If it is moving with V, when I say no force acts, it means what? If this one is moving with V, then its speed is not going to be changed by any of these remaining molecules, because separation is so large, no force is coming from these things. I continue with this point only. Molecules only exert force on each other. Molecules exert force on each other only when a collision takes place between them. So once in a while, when a collision takes place, definitely two molecules are moving, let's say, towards each other. So when they come in contact, no real contact takes place. When they come much closer, they are repelled. But this will be called collision. In fact, when I say my hands, when they clap, and as you hear the sound, so nothing is touching. This hand basically is not touching this hand. The electrons on the outer layer of this hand, electrons on the outer layer of this hand, once you come closer, they are going to repel each other. So we are not talking about that deep thing. So when I say a collision, then whenever a collision takes place between these molecules, they will exert force on each other, which is nothing but collision force, which we have already seen in the chapter of head-on collision and oblique collision. So they do not exert any force except when they interact, when they collide. And similarly, continue with the statement, and similarly, walls of the container exert no force on the molecules, except when a collision takes place. Except when a collision takes place. जो हमारा point था large separation, it is going to help us in this part, that if this molecule is moving and it doesn't interact with the other molecule or the wall, its speed or velocity will not change. Now, next point. All the collisions between molecules and those between molecules and the wall are perfectly elastic. All the collisions between the molecules and those between molecules and the walls are perfectly elastic. Now, why do we need this point? This is going to help us in, before that, note down the next point also, and then both these points I'll explain together. Right on the next point. We can all write these points together, but it will be easier for you to remember this way. So write down the next point. Collision time between the molecules and between molecules and walls is negligible. What is this point first of all? So when these two markers collide, the sound which is coming, you're not hearing the sound continuously, something like ooh, no, it just collides for a fraction of a second. So what we are saying, that this fraction of a second is nothing but negligible thing. So whenever a collision takes place, it happens in an instant. Whenever a collision takes place between a molecule and the wall, it's not that the molecule will come in slow motion, hit the wall, will remain in contact with the wall, and then is going to go back. No, the whole thing happens in just a fraction of a second, and therefore we say that this time interval in which the collision took place is negligible. क्यों हमने इस पॉइंट को बोला है? अब एक साथ देखना यहां पर. Suppose these are two molecules. This one is moving in this direction, let's say with speed of 10. This one is moving in this direction with the speed of 8. Now, assuming we have only one type of gas, they both are identical. I've already told you that coefficient of restitution is what? 1. Perfectly elastic collision. So if this collision takes place, This is 10, this is 8. Then let me see if you remember this. What is the velocity of this one? Answer this fast. What is the velocity of this molecule after the collision? Velocity of this one after the collision. Should not take fraction of a second to answer, if you remember the result. Good. This molecule is going to move. This molecule is going to move in this direction with 8. And this one is going to move in this direction with 10. Whenever a perfectly elastic collision takes place between two identical objects, perfectly elastic head-on collision between two identical objects, we simply interchange their velocities. So this 10, we give it to the second one, and this 8 is taken by the first one. Now, time of collision between these two, delta t. Let's not use the term of delta t because we will be using it somewhere else. Just remember the time of collision is negligible. So let's not introduce this delta t. Simply remember the time of collision is what? Negligible. Now, with this negligible thing, we can use a concept like this. These are two molecules identical, but you can see them in this form. I hope you can see the blue and the black. This is the blue marker and this is the black marker. And this one is moving with 10 and this one is moving with 8. So after collision, what happens? They collide, and then the blue one moves in this direction with 8 and the black one moves in this direction with 10. 10, 8, and then 8 and 10. हमने क्या बोला? हमने बोला एक काम करते हैं. Since you are saying that time of collision is negligible, let's use this fact that this molecule is moving with 10, it is still moving with 10, this molecule was moving with 8, this is still moving with 8, as if no collision took place. जो collision का time है वो कुछ है ही नहीं. अगर collision का time कुछ नहीं है, just imagine this. The moment this collision took place, suppose that very moment you blink your eyes. Just imagine करना. If you blink your eyes at that very moment and then when you open your eyes, what you found? You found that this thing is moving in this direction with 8. This thing is moving in this direction with 10. So what is the advantage? We can say that there is no change in the speed of this one. There is no change in the speed of this one. This is moving with 8. This one is moving with 10. फायदा क्या हुआ? जो बीच के collisions हैं इन molecules के बीच में, अब अपने को उनकी टेंशन लेने की जरूरत नहीं है. Suppose when the molecule moves from this position to this position before it collides with the wall, during that time when it was moving from this side to this side, during this time it suffered, let's say, 5 collisions. Now all these collisions took what? Almost negligible time. So instead of saying that collides and then it bounces back in this direction, this one moves in this direction, then this molecule interacts with some other molecule and all. So instead of saying this, what we say is this. This is coming with 10, this one is coming with 8, blink your eyes and they start moving in this direction. Forget about the color. Nothing is blue, nothing is black. They look what? Exactly same to you because they are what? Identical balls. So 10, 8, no collision took place. It moves in this direction with 10. It moves in this direction with 8. What is the advantage? We don't have to worry about intermediate collisions. We don't have to change their speeds. Something moving with 10 keeps on moving with 10 all the time. Something moving with 8 keeps on moving with 8 all the time. And यहां से यहां तक का अगर अपने को टाइम निकालना पड़ा अगर तो हम क्या करेंगे सीधा सीधा whole length divided by the speed. We can do this type of approximation if we say that collisions are perfectly elastic and they took place in what negligible time. Are you comfortable with this point? Yes or no? Fast and note down this figure. Let's write down this not extra point, just a statement to explain last 2 points. If we say that collisions are perfectly elastic, and time of collision is negligible, then we can assume that when a molecule moves inside the container, it keeps on moving with same velocity. Before it reaches the wall of the container. When it collides with the wall, its speed and direction both will change. But before that, the same molecule is moving from this place to this place. Right on, next point. Ideal gas is an isotropic gas. Ideal gas is an isotropic gas. That means it has same properties everywhere inside the container. What this point is, suppose you say that at this corner there are, let's say, 100 molecules. If you arrive at this corner and you take the same volume, you will find that it still has what? Same 100 molecules. So what basically we are saying that effect of gravity is not present on these molecules. Why do we need to mention this? If you talk about atmosphere, you know that density of atmosphere as you go up decreases. Why? Because of gravity. Gravity is pulling all these molecules down, and therefore density is much higher at the sea level than as you go up a mountain or some hilly area. But we are not taking a container whose height is of kilometers. ऐसा नहीं कि हमने अर्थ की सरफेस से माउंट एवरेस्ट तक के साइज का कंटेनर बना लिया. No, we are not interested in those things, and therefore we are saying is that if you take density of molecules over here at this place, at this place, at this place, at this place, it will be same everywhere. The other thing, when you say isotropic, it means if you find that right here there is a molecule which is moving with 10 meters per second, then over here you can also find a molecule which is moving with 10 meters per second. If you say that there is a molecule which is moving with 8 meters per second, then you can always find another molecule which is moving with 8 meters per second. That means no portion of this gas, no portion or the region which it occupies is spatial. Everywhere inside the container, things are completely uniform. That's the meaning of what isotropic. Now with the isotropic, let's also add one more point just for your understanding. The gas molecules, when they move inside, how do they move? One is moving in this direction, other one is moving in this direction, third one is moving in this direction. So if you talk about their velocities, so let me see if you understand this. If I tell you that things are isotropic and I ask you what will be the average velocity of all the molecules inside, what do you think should be the answer? Once I say things are isotropic, write down the answer in the comment box fast. What will be the average velocity? I'm not asking average speed, I'm asking average velocity of all the molecules inside the container. Answer this thing fast. I will take 2-3 minutes more. Let's see how many of you are going to answer this part. Not a single person. It should be 0. It should be 0, not a single answer. Why it should be 0? Suppose you say that average velocity of the gas molecules is 5 meters per second in this direction. Now imagine, if you say all these molecules have an average velocity of 5, that means the whole volume of the gas is moving in this direction. Does it happen? You have something inside the container, that container doesn't move on itself because the gas is inside. No, that doesn't happen. So what happens? If one molecule is moving in this direction with 10, you will certainly find another molecule which is moving in this direction with 10. If you have a molecule which is moving in this direction with 8 meters per second, you will always find a molecule which is moving in the opposite direction with same speed of 8. So if you go for average, then all these velocities cancel out each other. So this point, this thing will help us in doing what? That velocity distribution in every region is what? Uniform. Uniform means if there are 20 molecules moving at a particular time in this direction with 10 meters per second, in the entire container, you can always find 20 molecules which at that very moment are moving in this direction with same speed, so that on an average you get average velocity what? 0. Let's write down this point. This is the last point. Average velocity of all the molecules, average velocity of all the molecules inside the container is always 0. Average velocity of all the molecules inside the container is always 0. We'll discuss mathematical model in the next class based on these points. But if you are comfortable with all the assumptions, if you understand why did we take all these assumptions, then write down yes in the comment box and then you can leave. Thank you very much.